Okay, good morning, everyone. So it's my pleasure to introduce now Vikrant Jadhav. Vikrant received his PhD 3 years ago, 4 years ago, in 2022, from the Indian Institute of Astrophysics in Bangalore, working on star clusters and binary products under the supervision of Professor Subramanian. Then he moved for a brief postdoc in the Inter-University Center for Astronomy and Astrophysics in India, working with Professor Saha. And then his first postdoc abroad India was a Humboldt Fellow at the University of Bonn in Germany, working with Professor Pavel Kroupa. And right now, he got, since a few months ago, he got a postdoctoral position at the Charles University at Prague, continuing his work on the dynamics of stellar clusters, tidal tails, blue stragglers, and binary stars in general. So he works using both observations and N-body simulations. And today he's going to talk about one of his expertise, the blue stragglers friends, stellar interactions in a star cluster. So, Vikrant, when you want.
Thank you, Ore, for the introduction. Good morning. So today I will just give you our results about the blue stragglers and related post-mass transfer systems and star clusters. So the rough overview of the talk is basically I will first introduce about the formation and evolution of these kind of systems, how they are cataloged, and then I will go through some results. So whenever we looking at the stars in a star cluster, we get some information in bonus because all the stars in a star cluster have same metallicity, same distance, same age, and the only variable is the mass function. So we have different masses. So if you look at a star cluster in an HR diagram, you can see in the plot here. So most of the stars are in the main sequence, and then the more massive stars have evolved off, and they have become red giants or white dwarfs. So this is how a typical HR diagram for a cluster looks like, and this plot basically shows the evolution assuming single stellar evolution. So no binary interactions, nothing special is happening, just typical evolution. But in reality, there are like majority of the stars are in binary systems, like more than 50%. So stellar interactions are an important factor we have to account for before analyzing like any of the systems. And any deviations from these nominal tracks can be used to identify such systems and analyze them. So what a real system looks like. So that was just a picture, right? So this is a color magnitude diagram of a real cluster, M67. You can see majority of the stars are on the main sequence, and there are some red giant stars here. But you see there are some stars in this region, there are some stars here. So, and as I showed in the previous diagram, this upper main sequence should have evolved off into the red giants, but we still see some cluster members here. So how are they still alive? So the most viable method for their existence presently is they have gained mass by some mechanism. So they have been rejuvenated and they are alive for a little bit longer than what was expected before. Similar mass accretion can also happen along the main sequence. And if the star becomes, let's say, it becomes slightly brighter, then that will move within the main sequence, but it will not be noticeable. So that's why these stars are basically called as blue lurkers, while the stars which are above the turnout, they are called as blue stragglers because they are bluer than the cluster and they are obviously noticeable. When these blue stragglers evolve, of course, they go through their own subgiant phase and own red giant phase. And those kind of systems are basically called as yellow stragglers. They're basically the post main sequence phase of the blue stragglers. And all these stars, so I'm talking about stars less than 5 solar masses, so all of them end up as white dwarfs. So for a given cluster, we know what a typical white dwarf will look like. For example, in this cluster, the red giant branch is roughly around 2 solar masses. So the white dwarf form will be around 0.5 solar masses. So we know for a given cluster, all the white dwarfs should be 0.5 solar masses, assuming single stellar evolution. But we see, for example, in this cluster also, we see two white dwarfs are redder than the typical white dwarf region. So this is the typical white dwarf region, and two are redder. So redder here means they are less temperature and slightly bloated. So that's indication of lower mass. And also some clusters have higher mass white dwarfs, so they can be like more compact and higher mass. So why are such anomalous white dwarfs possible? Because look at this blue straggler. This is very bright. This mass is around like 4 solar masses. So when it becomes white dwarf, it will be more massive than the typical cluster white dwarf. So if we see any such like weird white dwarfs or any outliers outside the typical tracks, we can use them to study like the binary interactions. They are only possible via binary interactions. Uh, so this plot gives you a brief introduction about like how these interactions are happening. So I am only mainly focusing on binary interactions. Of course, the interaction can happen in triple systems or quadruple systems. The most simple interaction there is basically there is a binary here, and they simply merge due to external factors or internal angular momentum loss, and become a giant star, like bigger star, basically a blue straggler. And then when the blue straggler evolves, it can become a white dwarf, massive white dwarf, right? Because the mass of the blue straggler is more than the previous main sequence stars. Another aspect uh, by which this mass transfer can happen is, let's say, instead of having direct mergers, the two stars can stay separate. Let's say there is a giant donor and main sequence accretor. This main sequence accretor becomes a blue straggler and eventually a massive white dwarf, while the giant donor can become a normal mass white dwarf, because generally the core of the giant donor is fully formed, so the white dwarf of the giant doesn't change much. So we can expect like a massive white dwarf plus white dwarf as the final system. But if the donor was not on giant phase, it was, let's say, a main sequence or a subgiant branch, the core was not fully formed, then what happens is because of the mass loss during this exchange, the white dwarf formed by this donor becomes a lower mass white dwarf. So the main sequence accretor becomes a blue straggler and a massive white dwarf, but the companion is itself a lower mass white dwarf. So this lower mass white dwarfs or these higher mass white dwarfs or these blue stragglers, they are indicators of mass transfer systems basically. And whenever we are looking at stars, they can be in any of these phases. So they can be pre-interaction, just simple binary star. They can be merged systems, so they look like single stars. They can be actively interacting, so WMA type stars or X-ray emitters. And of course, they can be like isolated stars like uh, blue straggler plus white dwarf, etc. So we have to look for all different systems to understand what is the overall picture about this mass transfer happening. So how are these systems identified first? So as I said before, the HR diagram is like the one of the most powerful tool to identify these systems. Like it is the simplest tool, right? We can easily identify all the blue stragglers here. You can identify the unusual white dwarfs. You can identify yellow stragglers. Unfortunately, these blue lurkers cannot be observed, like identified using the HR diagram because they are within the main sequence, but other systems can be. Of course, we can use unusual abundances. So this requires some extra work. You need spectroscopy. But what happens is, let's say, in a merger, the accretion of a gas onto the star leads to heating of the atmosphere, and that can lead to burning of lithium, carbon, oxygen elements. So this depletion can be used as an indicator of the mass transfer history. Additionally, if the donor was a AGB star, then it can have higher elements, like high mass elements in it. And accretion of that material actually leads to enhancement in the S process elements. So for example, in this particular star, we can see the barium line is very strong, which is unexpectedly strong for this type of cluster. So you can say, okay, this particular star has gained some mass from an AGB type companion. Unfortunately, these kind of tests cannot be done for all blue straggler because not all mass transfers are happening in the AGB phase. And if the star is merger, you don't even know it's a binary. And sometimes this lithium carbon oxygen depletions are not detectable, or even if they are detectable, they are sometimes transient. So like they happen, they burn up very fast, and then sometimes they regain their original level. So the abundances are not 100% working criteria to identify the post-mass transfer systems. Another method we can use to identify these systems is basically you can create spectral energy distributions, SEDs. So as you know, like majority of the interacting systems are presently in binaries. So you can use a binary SED disentanglement to identify like two stars and their parameters. If you can calculate their radii, masses, etc., you can get some idea about what is the present day status of the system, and if that system is possible via like isolated evolution. If that system is not possible via isolated evolution, then we can say, okay, this looks like a post-mass transfer system. This is quick, but of course, it has lots of error associated with it. Like the error bars are typically too large compared to other methods. And the best tool we can have for this identifying these systems is of course spectroscopic binarity. If you have a radial velocity survey or light curves of the eclipsing systems, you can get much more detailed information about these systems. You can know about their exact masses, exact temperatures, even the internal structure. So that can be the most powerful tool, but this requires a lot of work, and this is not possible to do on scale. So you have to target like one system and focus all your work on that. So now that we know like there are these different techniques for using which we can identify these different types of post-mass transfer systems, first we need to create a catalog of them to understand how they behave. So how to create the catalog, that's what this slide talks about. So first of all, I will show you like what we typically use to identify blue stragglers. So they are the simplest systems out there. Uh, let's say this is a cluster isochrone where the most of the stars are lying. And in this blue region, slightly bluer and hotter than the main sequence turnoff, that's where the blue stragglers lie. And blue stragglers are the most obvious post-mass transfer system. So anybody who is interested in binary interactions, you can start here because you know for sure there was interaction here. And now we can do some extra analysis to identify like how the interactions are happening or how the changes are imparted due to the interaction. And this was like blue stragglers have been identified, I think, from 1930s. But in the early days, it was thought, okay, maybe they are just field stars. They look like just overlapping in the cluster. But with Gaia astrometry and the recent data, we can be sure that, okay, these stars are cluster members and they are post-mass transfer binaries. Post-mass transfer systems, not all of them are binaries. If you look at like a cluster populations, all clusters above 500 million years have blue stragglers. And the number of blue stragglers ranges like this. The equation is like it proportional to the cluster mass and the cluster age. You had typically like a handful of blue stragglers to maybe a 50 blue stragglers. And if you go to like omega sen, etc., you can have, of course, hundreds or like maybe 200 blue stragglers. That's the maximum number we have. And there are lots of papers in literature who have tried to identify these blue stragglers. Unfortunately, this is not that easy because let's say, so this is one of the globular cluster, and in globular cluster, the shape of the region is slightly different. But you can see, okay, this was a UVCMD, I think 275 minus 336 HST. So in this diagram, they have selected these blue stragglers. And if you plot the same blue stragglers on an optical color magnitude diagram, you can see the black dots are same. They are going outside this box, and some stars coming inside the box with these blue dots. In optical CMD, they look like blue stragglers, but in the UV CMD, they are not. So now the question comes like, which CMD do you trust? Unfortunately, there is no clear answer as of yet. So like you have to just pick one and like maybe give some less kind of probability for the other blue stars. But like this kind of things are still a problem in the field. The another systems which we can quickly identify using the color magnitude diagram is the yellow straggler. So yellow stragglers are, of course, instead of this blue region, you can look at this yellow region just above the subgiant branch and bluer than the red giant branch. So in this region, we typically find the yellow stragglers. So they are the subgiant phase of the blue stragglers. And if they are in a cluster, we can be sure, okay, they are also post-mass transfer systems. Presently, there are around like 1,000 yellow stragglers known in 400 open clusters and globular clusters. In globular clusters, the catalog is not complete yet because most of the HST studies only focus on the central region. So there are lots of missing classifications for these yellow stragglers. And compared to blue stragglers, yellow stragglers have been quite less studied, so there is no clear answer as of yet about what is the binary fractions or what are the abundance of peculiarities found in yellow stragglers. A few things have been noted. For example, a high chromospheric activity has been identified in few yellow stragglers, which is an indicator of some kind of mass transfer. And Of course, there are some contamination probabilities with yellow stragglers. Also, some bloated ongoing interaction systems can fall in the same region. So because they are like the systems are here, but they are bloated, they can come up and they look like yellow stragglers, or sometimes a blend of red giant star plus main sequence star, like unresolved binary. It can also fall in the same region. So we have to remove such kind of systems before doing the analysis. The next systems I will talk about are the blue lurkers. So as I told, blue lurkers are on the main sequence. They are post-mass transfer systems, but how do we identify them? So one thing we can use is that whenever recent mass transfer happened, it likely imparted some kind of angular momentum to the star. And for a given star, what is the typical rotation velocity for a given age and given mass. So if you see a star which is faster rotating than the rest of the similar stars, you can say, okay, maybe it had some kind of mass transfer event happen. So this was done in the beginning by Lina 2019. So they identified fast rotating stars in M67 cluster using Kepler data. We also extended the study to more clusters. And for example, in this cluster, we can say this is NGC 6811. So there are these three stars here on the color magnitude diagram. They're well within the main sequence. But if you look at the rotation periods, you can see these three stars have very, very fast rotation compared to the rest of the stars. So this is the rest of the cluster, which has rotation periods of like more than 10 days, but these three stars have very, very fast rotations. So they are very good candidates for being a blue lurker and a recent mass transfer system. Another technique which we can use to identify these blue lurkers is, instead of looking at the star itself, look at the companion. So as I told before, if you see a weird looking white dwarf, like high mass or low mass white dwarf, that's also indicator of a mass transfer. So what we can do is, here we can search for white dwarfs has unresolved companions. And if the white dwarf is very, very low mass, then that confirms that white dwarf was a donor in some kind of mass transfer event. And so the main sequence star, which is current companion, becomes the accretor. By default, that becomes a blue lurker. So currently there are around 130 blue lurker candidates known in around 40 open clusters of all ages, like 10 million years to globular clusters. And the number of blue lurkers is within a cluster are approximately equal to the number of blue stragglers. Like this is for only a few clusters, but the number of blue stragglers total is 1,000, and this blue lurkers is only 130. So the catalogs are very, very incomplete as of now. And the last type of systems which can be easily identified as post-mass transfer systems are the low or high mass white dwarfs. So for a given cluster, as I told already, that we expect a particular mass of white dwarf. So in this plot, this is a color magnitude diagram, and we can plot what a typical white dwarf will look like. So for example, the high mass white dwarf, 11.3 solar masses, they start as very compact objects and they cool down and they follow this kind of track. If you have a lower mass white dwarf, let's say 0.4 solar masses, it will start here slightly bloated compared to the higher mass one, and it will cool down following this track. So for a given cluster, we can calculate like the very, very early white dwarfs were 1.4 solar mass, of course. So they formed here and they are cooling down. And as they are cooling down, you can see like this colored lines show the ages of the white dwarfs. So the most massive white dwarfs have started here and they cooled down to here. The most recent white dwarfs, they are started here and they are still at the very, very bright phase of their life. So for a given cluster, the locus of all these previous white dwarfs creates some this kind of shape. For each cluster, the shape is slightly different, but overall it's like this. So for this particular cluster, Rupert 147, it has like around 13 white dwarfs associated with it, and you can see like most of the white dwarfs are falling on this region where we expect them to lie. But there is this one white dwarf which is an outlier. So this looks like a very, very low mass white dwarf for a given age. So again, this white dwarf looks like it formed after giving some mass to the companion. So we don't see the companion now. It may be like the binary may have been destroyed, like decoupled, like there are two stars now, or the binary is too faint, we don't know. But this particular white dwarf looks like a very good candidate for a post-mass transfer system. Currently, there are around 200 white dwarfs known as open cluster members with Gaia membership, and 36 white dwarfs are known, we identified them as lower mass white dwarfs, and four white dwarfs identified in the higher mass region, so in this region basically. So at a given age, they are more massive than the cluster what we expect. Unfortunately, again, like there is a very big contamination problem. So we found that in our analysis, out of these 200 members, 25% of them were contaminated. So they are like field white dwarf, just looking like cluster members. So if this statistics is correct, again, like these numbers are also likely to be like, you have to like very accurate. These numbers are also including this 25% contamination. So this is just to summarize to all these catalogs. So all these different stragglers, like of the blue stragglers, there are around 7,000 blue stragglers known in open and globular clusters. You can see they are typically in the upper main sequence, typically masses of more than 1 solar masses to up to 5 solar masses. Then there are yellow stragglers, which are in this yellow region, yellow color here, slightly cooler than the blue stragglers. We know around 1,500 of yellow stragglers. The blue lurkers are on the main sequence of open clusters, and there are around 130 blue lurkers here. And of course, looking at the white dwarfs, you can see like these colored white dwarfs here, they are like the lower or higher mass white dwarfs. So this is the present state of the whole field based on Gaia data, of course. So if you include HST data or some upcoming LSST data, this sample will be tremendously increased, because we know for sure the number of blue lurkers should be similar to number of yellow stragglers, and the number of white dwarfs within a cluster are like much larger, because most of the white dwarfs are fainter and they're not visible in Gaia. So there are lots of scope to increase, particularly the blue lurker and white dwarf populations. So now that we have the catalog, we can like move forward and try to understand how these different systems are there and like what are the properties. So I will just highlight some of our results. So to do most of our analysis, I have used Gaia data, test data, Gala spectroscopy, and one of the primary instrument I have used for my analysis is the UVIT, which is ultraviolet imaging telescope. So UVIT is a space-based observatory on board Astrosat. It has a spatial resolution of 1 arc second, field of view of 28 arc minutes, and aperture of around 40 centimeters. It can observe simultaneously in far AV and near AV bands. And in our survey, we basically looked at open clusters using multiple far AV and near AV bands to identify hot compact objects. You can also use the same UV data to analyze, let's say, star formation in nearby galaxies or supernova remnants. So the primary thing we did was the survey of open clusters using UVIT. So we analyzed around 14 open clusters so far. These are the names here. And we found basically the compact objects within these clusters. So in the HR diagram here, I have shown all the hotter companions we have found in these open clusters and like some globular clusters and the galactic field. So the hollow triangles are the main optically luminous components, and the solid triangles are the compact objects. So these are all the different kind of systems we found in open clusters. So they range from blue stragglers, yellow stragglers. These are horizontal branch stars. There are some stripped stars candidates. There are some hot subdwarfs. There are extremely low mass white dwarf, normal mass white dwarf. So all different kinds of compact objects could be found in these open clusters. So I will just highlight a few of them. So this is one of the very interesting blue straggler system, WCS 1007. It's a binary system inside open cluster M67. It was already known that this is a binary with period of 4.2 days and eccentricity of 0.2. So like significantly eccentric orbit. In 2019, we analyzed the UV SED of the system and the IUV spectra. You can see in this plot here. So these dots are the UV SED and the gray is the IUV spectra. And the gray line is the dark gray line is the blue straggler component. And you can clearly see that there is a significant UV access happening here. So this UV excess can be explained by presence of a white dwarf shown in this green plot. So this white dwarf can explain the UV flux. In our initial estimate was the white dwarf looks like around 0.2 solar mass, but as I said before, the SCDs can have very large errors. So we wanted to be sure whether this white dwarf is true or not. So we looked at the test data of this star, and we found that, okay, this looks like an eclipsing system, like in the preliminary analysis. Like this is the light curve you can see here. The two ellipses are sort of visible, but later analysis showed that, okay, this is not actually an eclipsing system. It's actually ellipsoidal variable. So the star is bloated, and it's non-spherical system. So that's why the shape light curve is changing. This is not at all eclipsing. But anyway, like we can try to fit the system even it's non-eclipsing. And using radial velocity and test light curve, we could we could get the parameters, and the masses of the stars were very well matched with the estimates given from the SCD. So this also tells us that, okay, the SCD parameters are trustable, and we can use those to do further studies. Another interesting thing about this star was this is also a delta Scottish star. So you can see this is this is the periodogram for the star, and you can see there are lots of oscillations happening around this 20 per day frequencies. So these are delta Scottish pulsations, and what we found is these pulsations are very similar to other delta Scottish stars. So there was nothing different about the pulsations. So for to give you context, this is a blue straggler system, so we know it had some kind of mass transfer event. And also this is ellipsoidal variable, so that means it's a non-spherical stars. But even if both these facts don't change the pulsation properties of the star. So it looks like just a normal pulsating star. So this, but again, it's only one sample, so we need to analyze more pulsating stars to say whether this mass transfer changes the pulsation properties or not. And the host cluster M67 is one of the most studied open clusters out there. In this particular cluster, this work was done by one of my master students. So you can see this cluster has 15 blue stragglers. All of them are mass transfer systems, 2 yellow stragglers, 3 high mass white dwarfs, 7 blue lurkers, 6 main sequence plus white dwarf systems. So they don't look like any mass transfer history, but okay, they're binaries. 11s process enhancement. So this was done using GALA data, and we could find excess in barium, yttrium, lanthanum, and more than 10 X-ray emitters. So X-ray emitters again are likely to be ongoing interacting systems. And if you look at the color magnitude diagram here, you can see the special type of stars are all over the HR diagram. So this is showing that our assumption about single star evolution and using that to identify to describe a cluster, it's not that accurate. There are significant number of systems which are interacting or their post interaction. So we'll just give you some numbers, within blue stragglers, 80% of them are in binaries, or 33% of the blue stragglers show S process enhancement. So that means that they are formed via AGV mass transfer. And another interesting thing we noted is this is a period versus eccentricity plot for all these peculiar stars. And you can see the periods range from, let's say, less than a day to 1,000 days. And the eccentricities range from 0 to 0.6, 0.7. So most of the binary interaction people, when they do simulations, they just circularize the orbit, because anytime mass transfer happens, the orbit is circular and everything is well and good. But we can see in reality, that's not the case. Most of the systems, there are few, maybe 5, 6, 7 systems with zero eccentricity, but most of them are actually highly eccentric. So this means that the eccentricity circularization is not approximation which we use everywhere. Of course, some people have said that dynamical interactions after the mass transfer happen can lead to eccentricities, but that's always not the case. So some of them can be eccentric and still have mass transfer. Another thing I would like to talk about is basically we can use these post mass transfer systems to easily understand what is the typical mass transfer efficiency in mass transfer systems. So because these stars are in a cluster, we know for a given cluster where the main sequence turnoff is and what is the most massive star present in the cluster. And we can also calculate the mass of these blue stragglers. And if you compare the mass of the blue straggler with the mass of the turnoff, you can see in this plot here. So of course, mass of the blue straggler is more than the turnoff always. And we can calculate a term called mass excess, which is the difference between the blue straggler and the turnoff mass divided by turnoff mass. And this term is basically equivalent to mass transfer efficiency. So in isolated interacting systems, you don't know this number at all. People like sometimes use conservative mass transfer, let's say 100%, some use 30%, some use 10%. If it's only the wind accretion is happening, it's even less efficient. But in observations, typically it's very, very difficult to get this mass transfer efficiency. But for blue stragglers, it's very easy. You can just calculate the mass. Like, of course, this is not accurate. This is just an estimate, but you can calculate this relatively easily. And you can divide the blue stragglers using some ad hoc classifications. For example, if the mass excess is less than 0.5, you can say this is like a non-conservative mass transfer event or like less efficient mass transfer. If the mass excess is within 0.5 to 1, so basically 50 to 100% efficiency, you can say this is sort of a conservative mass transfer, or it can be a merger event where most of the content was merged. But the issue comes when the mass transfer efficiency becomes more than 1. So this means that these particular blue stragglers require more than 2 stars for their formation. And if you just look at the numbers, so in my first study, I found the number of these 3 different classes was around 55 to 30 to 15. Then later, Kui et al. 2015 did similar analysis, and they found the ratio to be 45, 45, 15. Compared to that, like there was another study which used different method to estimate the stellar masses. In their analysis, they found that the ratio is around 80, 20 to 0. So they found none of this extreme mass excess blue stragglers. So every blue straggler was within like the less than 100%. So they did not require more than 2 stars for the formation. But they found in open and globular clusters, so this is open and globular clusters, the numbers are slightly different. So for example, in globular clusters, even more blue stragglers are in the lower efficiency regime. So, and the numbers here are quite different. So this means that the masses estimated for the blue stragglers have an issue. Just because 2 people use 2 different methods, the ratios are completely different. So we need to first make sure how to get mass of the blue straggler before doing this kind of analysis. And just to give you some extra information about this mass axis, so this particular plot shows the mass axis versus cluster mass. So you can see as the cluster mass is increasing, the mass axis is also increasing. So this means that in more massive clusters, we can have more efficient mass transfers, or you can have more interactions leading to more massive blue straggles. Of course, this is just because of the statistics also. You have more stars, so they are more likely to merge or more likely to interact. And that's what's likely leading to this particular plot. And another thing we can note is also, we can look at the same mass transfer things happening in time. So this plot shows the age of the cluster with the fraction of blue stragglers in this high and like low mass and high mass excess regime. You can see most of the clusters in the very, very young age, they are split 50-50. So 50% are conservative mass transfer, 50% are not. But if you look at the very, very old ones, you can see the majority of them are dominated by this low mass excess systems. So that means that in older clusters, less conservative mass transfer is preferred. So we still don't know why, but that looks to be the case. Like the older clusters have less conservative mass transfer compared to younger clusters. We don't know why. Another thing I would like to highlight is basically, as I told, like there was the WOCS 1007 was a pulsator. So to expand that study, we looked at all the blue straggler pulsators. Out of the 7,000 blue stragglers we have, we know that 100 of them are oscillating, typically like delta Scuti or SXP type stars. And this column magnitude diagram shows the typical blue stragglers, like the HR diagram position of them. Most of them are fast rotating. You can see in this particular plot, this is the period versus V magnitude. and their periods are less than 0.1 days. Compared to blue stragglers, these main sequence stars have slightly larger range of periods. But you can see like this is a in orange I have plotted the period luminosity relation for normal delta Scuti stars, and these blue stragglers seem to follow that in this region, but in the longer period region, the blue stragglers are slightly different than the expected period luminosity relation. So of course, first we need to increase the sample to say, okay, like just 4 outliers are not enough to conclude anything. But the one delta Scuti and M67 also showed no peculiarities, and this large bunch here also shows the pulsations are normal. So it looks like the mass transfer doesn't change the pulsation properties of a star. So that may be interested for field post-mass transfer systems. And to just go to the last step of the talk, we are currently working on getting fundamental properties like precise parameters for the blue stragglers, because I told earlier that the stellar masses are very important question that's still sort of unanswered. We don't know if the period luminosity relation, like the mass luminosity relation of a post-mass transfer system is uh, same as the normal main sequence stars or not. So to answer that, we are basically looking at eclipsing systems where we know for sure, okay, we can get the periods, we can get their masses, their luminosities very accurately. So there are around again 100 eclipsing blue stragglers. You can see here there are different classes, like EA means they are detached binaries, or they are EWs, which are like contact binaries. So all different systems are there, and the spectroscopic follow-ups are ongoing for these systems. So we want currently we are in the process of obtaining their ephemeris using Gaia and test data, and the light curve based fitting is ongoing. You can see here this is a these are the Gaia photometry for this particular blue straggler, and we can get the orbital properties and some basic parameters like temperature ratio, radius ratio from this fits. And now the next step will be to include radial velocities in this to get actual masses. And once we know about the properties of the stars, then you need to do simulations like using MESA or hydrodynamic simulations to understand are these systems physically possible to create or not. So just to conclude, I showed that there are many different straggler populations out there, and they compose around 5 to 10% of the cluster population. So all these 10% of the stars, they have changed their masses from the original numbers. They have changed their luminosities. Their chemistry is different than the previous ones. So this means that if the 10% of the stars are changed from the initial population, then the simple stellar population approximation, which is used everywhere, like in unresolved studies, it's not that accurate. So you need to account for the binary interactions and the changes made by those interactions in any kind of unresolved study. You can't simply use just put a cluster there and get the luminosity and masses at given age. That's not easy to do. That should not be done. Also, these post-mass transfer systems in clusters particularly are ideal targets to study stellar interactions because we know about their extra properties like ages, masses, etc., distances. So the cluster association is also an important thing which we can use to understand the overall binary interactions. So for example, in these clusters, we have binary interaction products from with periods of few hours to 1,000 days and eccentricities of 0 to 0.6. So in simulations also, we need to account for like these kind of systems, and you can't use approximations like all the interacting systems are circularized by definition. And just to give you some outlook, so I already showed you that there are different ways to catalog these systems, but all these catalogs have very, very large incompleteness and impurities. So we need better astrometry and like large scale astrometry, accurate astrometry to get refine the memberships. And the homogeneity of the data is currently like good for open clusters, but for globular clusters, it's still like you only see the central part or you see only the outer part using Gaia. So there is no homogeneity there yet. Even with LSST, I think the saturation issue will lead to like problems within the center. So only outer regions will be possible, but you need a better surveys. Maybe Euclid will help to get like homogeneous samples in globular clusters. And once we have all these samples, we need to, of course, look into multi-epoch spectroscopy or high resolution surveys to basically understand about them in detail. So that's it. So if you have any questions? Yes. Yeah.
Is there any question in the room?
Well, thank you. Very nice talk. So I have maybe two-in-one questions about the blue strikers fraction in globular clusters in particular, because I imagine that in this object where you have mass segregations, in particular in the one where you had the time to get mass segregation, you will also get a difference in the distribution of mass efficiency, of the mass transfer efficiency as function of radii. Is it something that we observed? Because I was a bit surprised with the results you were showing with the globular clusters where you don't see at all any very efficient mass transfer in globular clusters. I would actually naively have expected the inverse, that you get more very efficient mass transfer in the center of the clusters because you have the massive binaries, primary stars that sink inside the center of the globular clusters and will be there, and you will get an offset with the blue stragglers that you get in the outer part of the globular clusters. So
yeah, so like you can just look at this plot to get the idea about the mass transfer efficiency. So you can see that there are more stars near the turnoff. So they are the least low efficient systems, right? So just looking at the system, like just looking at the color magnitude diagram, you can easily see that the this population is dominant compared to this population where the mass transfer efficiency is high. So I haven't looked into the radial distribution of this yet, but it will be an interesting thing to look at. Yeah.
Any more questions? Thank you, Vikrant. Really nice review. Never heard of the blue lurkers. They were interesting to see. You talk about how the blue lurkers are found with rotation, peculiar rotation. Have you looked into the rotation of the blue stragglers? How's the situation there?
Yeah, so around 50% of the blue stragglers have fast rotation, 50% don't. So again, if they are merger products, there is like random number, like it can be fast rotating or not. And of course, when the blue straggler form, that's also an important factor. It can slow down after some time. So that's why I think only 50% of blue stragglers have fast rotation. So even if you look at like rotation within main sequence, you will not get all blue lurkers. You will get only the fast rotating ones. Yeah.
Okay. Thank you. Okay, so there is one question online, so go ahead.
Yes, I hope you can hear me.
Yeah.
Okay. Thank you for the very nice talk. That was really nice. So again, regarding these blue lurker stars that are rotating more rapidly than the rest of the cluster, are there any predictions for how many of these you should find in a given cluster, depending on the cluster mass or cluster age, like similar to what you showed for the blue stragglers?
Yeah, so for blue stragglers, we have this equation here. You can see number of blue stragglers is proportional to the cluster mass and cluster age. In blue lurkers, we don't have a complete catalog yet, but for example, in M67, we have 15 blue stragglers and 7 blue lurkers. And that's the most studied cluster out there. So if you assume that the mass transfer happening on the main sequence and above the main sequence is not that different, the numbers should be similar. So I think we should have, if we have 7,000 blue stragglers, you should have at least 3,000 blue lurkers. Yeah. So and also we analyze the rotation using Gaia ISO survey, and out of the number of stars we have that have spectra and the number of stars we could find fast rotation, the number is also similar. You should expect around few thousand blue lurkers out there.
Okay, thank you.
Yeah.
Okay. There is another question online, so please go ahead.
Hi, Vikrant. Thanks for the really great talk. I thought that was really interesting. So when you sort of showing this figure here on that you are referring to before, the color magnitude diagram, where you can see the sort of extension of the blue straggler stars. So so how does the mass function of the mergers come into play here, and how do you disentangle that from the mass transfer efficiency?
So the mass transfer of the progenitor is a problem because the mass function of the progenitors, because at presently we know about the actual mass of the blue straggler itself, and that's also not just approximate value. So we don't know yet about what are the progenitor masses. Typically we assume that one of the progenitor was a turn-off star and another progenitor is roughly of similar masses, and we most of the simulations people have performed found that if the mass ratios are like very low, then the mass transfer efficiency is not good. So I suspect all these blue stragglers they are formed from like similar mass binaries. So their masses will be similar to the turn-off masses itself. But I'm not aware of any study which has looked at like all the different mass choices for these progenitors. Does that answer your question?
Yeah, I think so. So you, yeah. So in the sense that the number of blue stragglers, or the number of sort of bright blue stragglers, tells you something about the mass transfer efficiency.
Yeah.
Yeah, you can say that, I guess, stars up in that region must be formed from high mass progenitors, right? So I think it's fair. Yeah, that's a good point. Thanks.
And anyway, you can assume that the mass excess is the lower bound on the mass transfer efficiency, because we like in that calculation, the both progenitors were assumed to be turn off. So if one of them was not turn off, like it's a smaller star, then of course the mass transfer efficiency will be increased. Then so the numbers I gave, they are basically the lower limits. That's what you can consider anyway.
Okay, thanks.
Okay, there's another question here.
Hi. Well, I would like also to thank you for your talk because it was very clear. I actually learned a lot. So I have two questions. So the first one is that I saw that in the M67, you found 33% of stars with S-process element enhancement. So that means that there are some systems that in which the primary star does not reach the AGB phase, I guess. But my question is, do you know if there are any other chemical peculiarities that we know already for those systems that does not show this process enhancement? But that, I mean, to be able to identify binary systems with respect to single stars in which you also don't see this process enhancement.
So unfortunately, we did not find anything conclusive. So there was another study which looked at lithium particularly, but they found that most of the blue stragglers have normal lithium, so no changes in lithium, and this S-process also like only 33% have. So like there is no single unique like trick which they can use to identify these systems. Yeah. No.
Okay, and the second question is about the binary fraction. Would you expect this to be universal or not necessarily?
I think it like depending on the cluster, of course. So for globular clusters, people like the binary fraction is slightly less, so maybe like 50 or something, like even or lesser. But for open clusters, I think this 80% number is true for at least two open clusters for which we have good data, NGC 188 and MC7. So I think this like the for open clusters, this 80% should be universal. Yeah.
Okay, thank you.
Okay, any more questions in the room or online? Okay, so if not, let's thanks again the speaker. That's all.
Thank you.
For the next week, there is no seminar colloquium, so you need to be here on Thursday, next Thursday. Enjoy Carnival, I guess.